This is more a conceptual one. We know that the work function is 4.37 electron volts. So how would it look like in terms of the number of ejected electrons versus intensity if your wavelength, or so your photon, is 5 electron volts versus the photon of 3 electron volts? Okay. Yeah. So this energy of the photon is higher than the work function, so you have enough energy to go over a threshold. So what you should find is that then you see, if you have one photon, then you have one electron ejected, and so on and so forth, right? So you see the same thing. Whereas if you have something that is less than the threshold, it really doesn't matter what the intensity you put in there, you're not going to see any ejected electrons at all. Right? Same thing that we had before. But now it's just in the graphical format. Yeah. Let's see what else. How about this one? The y-axis is kinetic energy of ejected electron, and the x-axis is going to be the frequency, so this is the frequency of the photon. And my hint for you is the energy is equal to h times frequency. So frequency, wavelength is inversely related. So how would this look like? Actually, can you? Yeah. So, yeah. Yeah. And higher energy means larger frequency or smaller frequency? No, high energy means high frequency. Yeah, it's the other one was inversely related. So if you have to draw a graph like this, then you should know that at some point there's a threshold somewhere. So just kind of draw randomly a threshold that's equal to your work function. If your frequency is small, is your energy high or low? Yeah. So what would be kinetic energy of the electrons? 0, no less. 0, 0, 0 is going to until reach the threshold, and it's basically the same graph that we had from the previous example. Right. So this is low energy, and this is your threshold. And beyond the threshold, then you should start to see your electron moving faster and faster and faster. So this particular graph is the same as the one before. H times frequency, yeah. Energy equals to Planck's constant times frequency. This is actually a question that I got directly from your textbook. Do you actually understand what's happening?
Yeah. I mean, I feel like they want you to do the same series of the same equation for both lasers.
Yeah, so essentially you have like one of those laser thing, and when the light comes in, when there's a laser light, then electrons, there's a photoelectric effect going on, and as long as the photoelectric effect is going on, the alarm is going to not sound. So what you want to do is you want to substitute, you want to walk across it But if you walk across it, of course, the light disappears, and then the alarm would sound. So what you're going to do is you're going to try to put in, as you walk into it, you're going to shine a laser beam onto the sensor to fool the sensor itself using a laser. So this is let's see, you're trying to fool the laser beam. One of the reasons I write my own questions because sometimes the question in the book is rather whimsical. So I tend not to use the whimsical one. Yeah. 9.11. 9.109 times what? 31 kilogram. Actually, 34 grams and 31 kilograms, same thing. So yeah. 31. 31. Yes, the 32 is a typo, so it's supposed to be 31. Yeah. So let me change that actually. Never mind. That's all right. It's material, but not too big of a deal. So essentially, it's there's a reason why I introduced the 1240 equals to energy of your photons in electron volt times the wavelength in nanometer. Partly because this is the unit that you're going to work most of the time. So equals to the energy in terms of electron volt times the wavelength in the unit of nanometer. So essentially, if your work function is 2.39, let's say your energy is 3 electron volts, then the wavelength is just 1240 divided by 3. So it's a much easier and kind of convenient conversion factor to use. So if the unit is in 3 electron volts, the wavelength of the light is 1240 divided by 3. This is 413 nanometer. 1240. Yeah. It's the same exact thing what you have before, which is E equals to HC over lambda. So E times lambda is equal to HC. It's just a convenient conversion factor. Just because we're going to use electron volt quite a bit. So yeah. So in this particular case, the question is, which of your laser is going to have sufficient energy to go beyond the threshold? So in this case, your 694, if the wavelength of your laser is 694 nanometer, then the energy of this particular wavelength is 1240 divided by 694. It's going to be 1.79 electron volts. Whereas your second wavelength is 405 nanometer. Anthony, are you looking for that particular equation, so the conversion factor? Should be around page 10ish, 8 or 10ish is yeah, on that. Is it in it? Type the number. So anyway, one of the conversion useful conversion factor is the 1240. So that way you can figure out the energy fairly quickly to electron volts. This particular problem is just a unit conversion factor. So let me continue with this particular question, and just kind of, I'm going to set up the problem, but I'm not going to try to solve all the math because it's going to be kind of annoying. It takes a lot of time. But the question is, the second part of that question, so on the last question on that particular page, is what is the velocity of electron ejected? Right. And what you know is that, well, it's a photoelectric effect, so energy of the photon is equals to the work function plus kinetic energy of the electron. And the good thing is that as long as you know the energy in terms of electron volts, you've already figured out that the wavelength of 405 nanometer have an energy of 3.06 electron volts. And you also know from the questions, the setup of questions, that the work function is 2.93, was it 97? 93 electron volts. And this is going to be, the sum of all of these are going to be equal to the kinetic energy of the electron. Well, if the question is asking for kinetic energy, I'll be fine with electron volt. But the question is asking for velocity. Yes. Hopefully it's all right. Okay. Yeah. No worries. No worries. We'll be here for a while, so. Yeah. No worries. So let's just continue on this one. The kinetic energy of the electrons algebra is going to be 0.09 electron volts. Is the kinetic energy of the ejected electron. But the thing is that the question is asking for the velocity. That's when you have to do some more unit conversion. So the kinetic energy of ejected electron is 1/2 times mass of the electron times velocity squared. But the thing is that this particular equation has to be written in joules, so you have to do unit conversion a bit. This is 0.09 electron volts times 1.609 times 10 to the negative 19 joules per 1 electron volt. So I think in terms of the skill that you know, it's not that complicated. It's just a lot of number crunching, which is never the fun part of learning anything. So velocity squared is equals to, I'm going to multiply these two numbers together. .14481 times 10 to the negative 19 joules divided by mass of the electron times 2. So it's just a bit of an algebra there. And if you look at your sum of your constant, you'll find that the mass of the electron is 9.11 times 10 to the negative 31 kilograms. I'm just going to divide those together now. So you'll find that the velocity squared is equals to 0.03 179 times 10 to the negative 19. Remember, joule is equals to meter squared per second squared times a kilogram. So if you divide joule by kilogram, the kilogram disappears, so you end up with a unit of meter squared per second squared. Yes, so joule is equal to that. That's a 2. Yeah. We're almost there. So the velocity in order to find the velocity, we have to take the square root of this whole thing. Let's see. Square root of 0.03179 times 10 to the power negative 19. And it comes out to an incredibly small speed of 5.638 times 10 to the negative 11 meter per second. At least in this particular problem, that's what we got. Yeah. Actually, 10 to the negative 11 meter per second was an incredibly small speed, so the alarm would still ring. But, oh well. This one is literally I copy pasted from the thing. All right.